Hello, I am Suresh Kuri from Department of ENC, Octavian of Technology, Belagavi. Let's learn about convolution encoding. Convolution codes are generated using discrete convolution of the message sequence with the generator sequence from the encoder circuit. Convolution circuits are basically defined by three parameters n, k and m. N indicates number of code bits generated per unit time. K indicates number of message bits inputted to the encoder per unit time. M indicates number of stages of shift, which is equal to number of flip-flops in a shift register. It's defined by two parameters. One is constraint length given by m into n and rate efficiency given by k by n. An example of a convolution encoder with n equal to 2, k equal to 1 and m equal to 2 indicates that number of bits generated per unit time. 2 bits are generated per unit time, so n equal to 2. Only one message bit is inputted to the encoder per unit time, so it is k equal to 1. And there are two flip-flops. There are two flip-flops in a shift register, that is m equal to 2. So n, k, m, three parameters will define the encoder circuit. So examples, more examples wherein it's a 2-1-1 encoder wherein there are 2 bits generated per unit time. K equal to 1, only one message bit is inputted per unit time, and there is only one flip-flop, only one memory element, so m equal to 1. Likewise, 3-1-2 encoder, 3 bits are generated per unit time. Okay. Only one message bit is inputted per unit time, and there are 2 flip-flops, so m equal to 2. 3, 1, 2. Likewise 2-1-3, 2 bits are generated per unit time, only k equal to 1 and m is 3 flip-flops. This is a 4-1-2 convolution encoder wherein there are this is 2-1-4 convolution encoder. This is 2-1-4 convolution encoder. 2-1-4 convolution encoder wherein 2 bits are generated per unit time, k equal to 1, and there are 4 memory elements, 4 flip-flops. Okay, 2-1-4. So likewise, convolution encoder is defined by 3 parameters n, k, m. Let us learn how to generate code words from the convolution encoder. Convolution encoder generates codes using discrete convolution of message sequence with the generator sequence from the encoder. Message bits can be of certain length, which is given by L bits, and the generator sequence is related to the size of the shift register, and number of bits in the shift generator sequence will be m plus 1. N indicates number of code bits generated per unit time, and each of these bits are generated by the convolution of message bits with the corresponding generator sequence. So C1, the first bit of the convolution code is generated with the time convolution of message with generator sequence of the first output. Likewise, time convolution of the second, time convolution of the third, so on up to time convolution of the n outputs, that is n parameter n. So there will be n generator sequences, and accordingly the time convolution is done n times with the message to generate the corresponding outputs. And when the commutator operates, all these n bits are generated for the message bit inputted. Likewise, these message bits are inputted to the encoder per unit time, and they are convolved with the corresponding generator sequence, and the code bits are generated, and when commutator is operated, these n bits are sent on the channel. Okay. So that is how the code bits are generated continuously. So for a message of length n, for every unit time, whenever a commutator is operated, we generate n bits. Okay, we generate n bits. So wherein the first bit of individual code bits are sent on the channel when a commutator is operated for the first unit time, then second unit time, third unit time. Likewise, depending on how much is the length, okay, it is those many brand codes. These are called brand word. Okay, whenever the commutator is operated, the number of bits sent on the channel is what we call number of bits sent on a channel per unit time is called a brand word. So how much is the length of the message, though many brand bits are generated and sent on the channel. So number of brand words generated will be in general m plus l, where m is number of memory elements and l is length of the message bit. Generator sequence are obtained from the encoder diagram. These generator sequence basically indicate the connection of the message input and the flip-flop outputs to the modulo 2 adders. For example, it's a 212 convolution encoder, wherein this generator sequence for the first bit is basically the connection. It indicates the connection of the message input and the flip-flop outputs to the corresponding modulo 2 adder. Now in this case, the message input is connected to the modulo 2 adder, and both the flip-flop outputs are connected to the modulo 2 adder. So hence it is 1 1 1. So generator sequence 1 is 1 1 1 because all three are connected to the modulo 2 adder. Whereas for the second, it is 1, no connection from the first flip-flop output, and hence it is second bit is 0. So in third, it is connected to the modulo 2 adder, so it is 1. So 1 indicates connection, 0 is no connection. So likewise, generator sequences are generated for every bit of the convolution code generated here. So likewise, the generator sequences are basically indicating the connection and no connection of the input and the flip-flop outputs to the modulo 2 adder. So in general, the generator sequence will have m plus 1 bits, and number of generator sequences will be equal to n. Now let us learn how the convolution codes are generated. Convolution codes are generated in two approaches, time domain as well as transform domain. So time domain operation is simply the time convolution of the message with the generator sequences. Now this requires convolution operation n times, and then interlacing the bits happens, and that is a long process. Hence, this convolution operation is translated into matrix operation, wherein a generator matrix is obtained from the generator sequences. Now in general, the generator matrix will have L number of rows. L is number of message bits, and number of columns will be n times m plus L, total number of columns. So size of the matrix is L cross n times m plus L is the size of the generator matrix. Now how is the elements of the generator matrix obtained? Now if you look at these elements, there are n generator sequences, and the first bit of all the n generator sequence is one set. Second bit of all the generator sequence, third bit of all the generator sequence. Likewise, every generator sequence will have m plus 1 bit. So last bit, that is m plus 1th bit of all the generator sequence. This forms the first row of the generator matrix. And all further rows of the generator matrix are obtained by shifting these first row, okay, by one brand word, okay, by one brand word. So this first bit of all the generator sequences is shifted. Second, again it is shifted. Third shifted, likewise up to m plus 1. Similarly, for the third row, again this second row is shifted one more brand word position towards the right, and it is third row is obtained. Likewise, number of rows in the generator matrix is equal to number of message bits, okay, that is L number of bits, L rows, and all the blank positions are filled with zeros, okay, all the blank positions are filled with zeros. So this is generator matrix for time domain approach of generating convolution codes, and the convolution code is simply obtained by matrix multiplication of the message sequence with the generator matrix. An example of a 212 encoder for which the generator sequence is 1 1 1 for the first bit and 1 0 1. And message, let us consider the message 10110. So the generator matrix for this convolution encoder is first bit of both the generator sequences. First bit is 1 here, this first bit of the second is also 1, so 1 1. Second bit of the first one is 1, and second bit of the second generator sequence is 0. So second block word is 1 0. So third bit is 1 here, third bit of the second generator sequence is 1, so third block word is 1 1. So this 1 1 1 0 1 1, okay, are shifted one block word to the right for the second row. So 1 1 1 0 1. Similarly shifted for third row. So likewise, number of rows in the generator sequence will be equal to number of message bits. So 5 message bits here, 5 rows, and all the blank spaces are filled with zeros. So generator matrix for the given convolution encoder. Okay. Then the code word is simply obtained by multiplying message with the generator matrix. So message is 10110 and the same generator matrix. By multiplying this, okay, and modulo 2 addition for every column, we generate 1 1 1 0 0 0 0 1 0 1 1 1 and 0 0. So total number of bits in the convolution code is n times m plus l. So in this example, there are two flip-flops, n equal to 2. 2 bits are generated per unit time, so it is n equal to 2. 2 flip-flops, m is 2, and the message length is 5, so it comes out to be 14 bits. We have 14 bits here. So this way, convolution codes are generated using time domain by simply multiplying the message with the generator matrix. It's a time domain approach of generating the convolution codes. Equivalently, we can generate the same convolution code in transform domain, and we have learned that convolution of two sequences can be done both in time domain as well as in transform domain. And also we have learned in signal processing concept that convolution in time domain is equivalent to multiplication in transform domain. Hence, the two signals to be convolved are represented in the form of polynomial. So the two signals to be convolved are message sequence and the generator sequence. So each one of these are represented with polynomial representation. So for the same example, we have the message polynomial, message sequence 10110, and this is represented in the polynomial form 1 plus x2 plus x3. Similarly, the generator sequences are 111, 101, and they are written in the polynomial form 1 plus x2 and for 101 it is 1 plus x2. And we have to perform the convolution of d of x and g of x in transform domain. So convolution in transform domain is simply multiplication of d of x and g1 of x. So the first bit of the convolution code is simply the multiplication of the message polynomial with the generator polynomial. So message multiplied with generator polynomial. So if you multiply and cancellation with the modulo 2 addition concept, what we arrive at is 1 plus x5. Okay, this is the first bit of the convolution code. Similarly, for the second bit, okay, we should perform the convolution of the message with the second generator sequence in transform domain, which is nothing but multiplication of the message sequence, multiplication of the message sequence with the second generator sequence. So when we multiply these two, what we arrive at is 1 plus x3 plus x4 plus. Okay, so these are the two separate bits, convolved bits of at 2 points, and interlacing of these has to be done with the equation given by the final code polynomial is obtained by c of xn. So in this multiplied polynomial, every x has to be replaced by x power n. So c1 of x power n, c2 of x power n multiplied with x, c3 of x power n multiplied with x2, so on up to cn of x power n multiplied with xn minus 1. So if you evaluate this expression, we arrive at the code polynomial and translate into bits, we get the convolution codes. For the given example, let us multiply. We have multiplied already, and substitute those in the given formula. So code polynomial c of x is x power 2. So since n equal to 2 here, so n equal to 2, it is x2 for the c1 x2 x c2 x2. So in this c1 of x, 1 plus x5, every x has to be replaced by x power 2. So 1 x power 2 power 1 plus x power 2 power 5. Okay, so every x has to be replaced by x2, and x times every x has to be replaced by x power 2 in this c2 of x. So by manipulating this, we arrive at 1 plus x2, x7, x9, x10, x1, converted into bits again. 1 plus x plus x2, then directly x7, okay, 1 x, x2, x3 is not there, x4 is not there, x5 is not there, x6 is not there, so x7 is 1, x8 is not there, x9 is 1, x10 1, x11 1. And when you look at this convolution code, this is same as what we have obtained using time domain approach. So the two codes which are obtained in time domain and the transform domain, they are the same here. So 1 1, here also 1 1 0 1 0 0 0 0 0 1 0 1, okay, 0 1 0 1 1 1 1 1 0 0 0 0. Hence convolution codes can be obtained both in time domain as well as in transform domain. Similarly, one more example has been solved. Okay, instead of giving the encoder diagram, okay, if generator sequences are given, then we can construct the encoder diagram. So given the encoder diagram, we can generate the generator sequence, or given the generator sequence, we can get back the encoder diagram. So this is our other approach, wherein there is a 312 convolution encoder with a generator sequence given by 110, 101 and 111. Okay, and since it is 3n equal to 3, k equal to 1, so the constraint length is given by mn, which is 6, rate efficiency is given by 1 by 3. This example is from one of the question paper, wherein if you look at this example, consider a 312 convolution code using the generator sequence given by G1, G2, G3, okay, with 110, 101 and 111 respectively. Find the constraint length, rate efficiency, draw the encoder diagram, find the generator matrix, and find the code word for the message sequence 11101 using both the time domain as well as transform domain approach. Okay. This is an example from the question paper which has been solved here. Okay. Now the first part here is constraint length is m into n, rate efficiency is k by n, 1 by 3. Now encoder diagram. Okay. Now n equal to 3 here, so there are 3 bits generated per unit time. So there are 3 modulo 2 adders, and k equal to 1, so only 1 bit is inputted to the encoder per unit time. And for the first bit, the inputs connections for G1 are 1 1 0. So first bit is from the message, and second bit is output of the first flip-flop, and since third bit is 0 here, no connection from the second flip-flop output. For the second one, it is 1 0 1. So this is 1, and no connection from the first flip-flop output, and third bit is 1, so third flip-flop output is connected. And for G3, it is all 1 1 1. Message input, first flip-flop, second flip-flop output. Okay. So this way, given the generator sequences, we can draw the encoder diagram. Okay. Or given the encoder diagram, we can write the generator sequence. Both are possible. Now the next part here is get the generator matrix. So generator matrix, getting the generator matrix is very simple here. So the first block word is first bit of each one of the generator sequence. Now first bit of G1 is 1, first bit of G2 is 1, first bit of G3 is 1. So 1 1 1 is the first block word. Then second bit of G1, second bit of G2, second bit of G3, 1 0 1. So that is a second block word. Third bit of G1, third bit of G2, third bit of G3. So this is 0 1 1. Okay. So that forms the first row, and since message is of length 5 bits, there will be 5 rows, and all these rows are simply obtained by right shifting of its preceding row, and all the blank spaces are filled with zeros. Okay. So generator matrix. Then generation of the code word in time domain approach. Okay. So it is simply matrix multiplication of the message with the generator sequence, and the first row, second row, third row, fourth row is multiplied with 0. So we'll have to consider first row, second row, third row, and obtain the bits. So this is the convolution code, okay, using time domain approach. The same code can be obtained using transform domain as well, wherein it is the message and the generator sequences are represented in the form of polynomial, and then each one of these generator sequences are multiplied with the message, okay, like explained in the previous example. So we got the first convolution bit in polynomial form, second bit and third bit, and these are interlaced using this relation. So since n equal to 3 there, every x is replaced by x power 3, okay, and x multiplied by second, x2 multiplied by this. So when you manipulate these polynomials, we arrive at finally the polynomial in the increasing order of power. When converted to bits form, we get the convolution code for the given message. And if you compare these two convolution codes which are generated using both the time domain, this is time domain, it is transform domain. So block words 1 1 1, 1 1 1, 0 1 0, 0 1 0, 0 0 1, here also 0 0 1, 1 1 0, 1 1 0, 1 0 0, 1 0 0, 1 0 1, 1 0 1, 0 1 1, 0 1. So likewise, we can generate convolution codes both in time domain as well as in transform domain. So this part is convolution encoding. Thank you. If you like it, you subscribe the channel. Thank you.